continue our discussion from part 3 in which we showed how to model a gold core with a concentric homogeneous shell of index of refraction N2. We're going to extend this to count for shells that are representing heterogeneous inclusions, for example, biolayers or proteins binding to gold particles. Now, if you really want to model the electrostatic interaction between a protein and a gold particle, you should look at a library called PyGVE. These effects can really be understood in the near field. However, those approaches don't scale, and so we're going to retain a coarse grain model for this system. And essentially what that means is we're just going to treat these as spheres that form a shell similar to N2. And the shell is going to be a mixture of N2 and the medium, which is air or water or whatever the medium is. So you can think of the heterogeneous shell as some mixture N0, which is equal to a combination of N2 and the medium, which is air. Okay? So coming back to the same configuration I had in part 3, I'll go to my shell material, and we'll choose a shell material, and because this is a mixed material, we're going to come to the composite materials adapter, and we want to pick spherical inclusions in a concentric spherical shell. The inclusions represent the proteins or whatever spherical molecules we're modeling. The inclusions are material 1 and the medium is material 2. Now our medium throughout this is air, so again I have to change material 2 to be air. I added air to the materials adapter since the last tutorial, so now you can just pick air rather than choosing a constant dielectric and setting it to 1. So here is air, just a shortcut. For material 2, it's a good question, how do you model a protein as a sphere? Well, you can look at the index of refraction for some proteins, but that information isn't always available. When we were studying an albumin protein, we found that for the most part the protein was about 5 nanometers in diameter, but it was actually closer in shape to a triangle. We did build a shell filling model for triangular inclusions, but because we're using such a coarse grain model, it's not really going to make a huge difference with the shape of these. It's more about the fill fraction and the index of refraction that you use. When data isn't available, it might not be a bad idea to use the index of refraction of glass. For a couple wavelengths, we found that it agreed pretty well to some of the reports for proteins, but I don't know if this is generally true. So I'm going to keep material 1 as glass. And we can go ahead and set the shell thickness again to 5 nanometers. A 5 nanometer thick shell corresponds to a protein that's about 2.5 nanometers in radius. Or in other words, maybe it's easier to visualize something like this. So this is our shell containing spheres. And each one of these spheres' radius is determined as half the shell thickness. Well, I said the protein had a diameter of about 5, so let's make the shell thickness 10. We see that certainly that does have an effect on the permittivity. And we also need to consider the fill fraction of the shell. So this is not the same as the fill fraction of the nanoparticle layer, but we can treat it with the same mixing model because this mixing model is built for spherical inclusions, and our shell has spherical inclusions. So you see that when there is no protein in the shell, then the shell can be treated fully as air, which is the same as the medium material. Excuse me. But as we add proteins to the shell, it changes the permittivity. And up here it's going to show us, we have to set the inclusion radius to be the same as the shell thickness. These should probably be linked, but I'll set that to 5. And so it shows us how many proteins could fit in the shell. For example, we've occupied 9 sites with this fairly large protein right now. We can also see what effect this would have on the extinction cross-section. As you see, the proteins, or in this case the glass inclusions, tend to cause a right shift in the plasmon resonance, which is the cornerstone of biosensing. And the reason this looks kind of sharp is because I'm using the Johnson and Christie dielectric function for gold. I forgot to switch it back since the last tutorial. And again, the same relation between the extinction cross-section and the reflectance holds. Same with the transmittance. So when people use biosensors, essentially what they're doing is they're binding stuff to gold, and that induces these shifts in the transmittance or in the reflectance.